Hello friends, welcome to our channel. Let's have a look at problem 3373. Maximize the number of target nodes after connecting trees. So this is the second of such problems. So here in this video, our strategy will be do graph coloring. So we're going to use two colors. So we can term them as 0, 1, or you can think of like black, white, or red and yellow. Something like that, right? So such that the adjacent nodes have different colors, right? So first I want you to notice these 3 points. So once you notice these 3 points, I guess solving this problem should be easier. First is that if in the same tree, if 2 nodes A and B have the same color, then the number of edges between any of the 2 such nodes is even, right? There will be even number of edges. So if they have different colors, the number of edges between them should be odd, right? Notice that in this problem, actually, what we have is a tree. So tree is a singly connected one, right? So always there is a path between any 2 nodes. This is the first point. The second point is that if we connect a node A with color 0 in tree 1 with a node B in tree 2, right? Then because if we connect using one edge, right? So if node B have the same color as A, right? Then all color 0 nodes in tree 2, so same as A, right? Has all the path lengths with A. And hence all the color 1 nodes in tree 2 have even path lengths with respect to A. So similarly, if node B have opposite color, let's say 1, and then all the nodes in tree 2 with color 1 will have odd lengths with A, right? And all color 0 nodes in tree 2 have even path lengths with A. So this is actually our key observation, right? The third one is that how to get the max number of targets, right? So first, it should include the same color nodes in the first tree, right? So we first find all the same color nodes in tree 1 as A, right? Let's call this N from the first tree. Then we find the large count of colors in B. Let's call it N from, say, tree 2, right? Then the result will be N from tree 1 plus N from tree 2. So here is a comment. For example, if color 0 count is larger in tree 2, then we connect A with any color 1 node, then in tree 2. So then this all color 0 nodes will have even length with respect to the corresponding nodes in A in tree 1, right? So notice that this comment also says that, so if you want to connect the one node with respect to the node in the second tree, it's not unique, right? As long as the color, the connecting color, either different or the same, then the one which is different from the connecting color will have even length with respect to the node in tree 1. So this will be our main thing. So with this slide, actually, we should know how to do the coding. So here we have 2 examples. These examples are very good because they have some illustrations, right? So for example, if we have 0, then all the nodes with respect to 0 have odd lengths. Then if we want to have so you can see in this one, if you do the coloring, so you always have 2 same color, 2 other color, right? Then you can connect with any node. The result will be the same, right? So here, actually, M and N can be as large as 10 to the power 5. Therefore, we cannot do it just using brute force. Like you can see the hint, right? You can compute this even U or odd U, right? So if we do this, actually, it's not very efficient. So what we want to do is that we color the tree, first one and the second one, and then we count the different colors in each tree, And then for a node, so we get the same color nodes in the first tree, and then we get the larger color count in the second tree. Then we add these two together. So this will be the answer I. So next, I guess we should carry out this program. Also, from this video, I want to demonstrate some general rules of reuse code. First, the two trees given by edges 1 and edges 2. So we can use this to construct a graph data structure. We can use adjacency list, right? So here, let me first get this m and n. So m will be the number of nodes in tree 1. So I'm going to edges 1. So notice that for a tree, the edge is exactly 1 less than the number of nodes. So here I'm going to add it by 1. So the length edge is 2. So also add 1. So next we are going to define two functions. The first one is build a graph, right? Given the edges, so edges or the number of nodes. So let's call it say k. So we build the graph. Another one is we want to color the graph. Color graph. So because tree is always we can color them using two colors. So actually this is called by partitioning of the graph, right? So we can have a graph. So it is not DF, right? So graph. And also, if to be explicit, I also want to put the number of nodes. Then what we want to do as basically is, once we have this two, so this let me first finish these two functions, and then we can see the logic. So build graph is actually rather straightforward. So here I'm going to, for each node, so and it corresponding to a neighbors, I'm going to use a set. But this is in comparison with adjacent list. You can use a two-dimensional array, but here using dictionary is also okay. So for I in range k, k will be the number of nodes indexed, zero indexed. So once we have this, then we're going to iterate. So for uv in edges, so graph u at v, and graph v at u. Then what we want to do is to return this graph. The graph is a dictionary, right? So the k will be the nodes, and the value for each of the k will be the number of neighbor sites, right? So then how do we do the coloring? So for a graph with n node, so we are going to do this. First, do some initialization, right? Then we are going to assign the color to say index 0 up to index n-1. Originally not assigned yet, so we use -1, or you can use none if you like. So the color we are going to assign two colors. It does not matter which is assigned to which, but you just need to know separate the two sets. So count will be 0, 0. So it's how many color 0, let's see, and how many color 1, right, respectively. So this the first component is for the count of color 0. The second one is for the count of color 1. So here we can do we can write a nested function to do DFS. So you can understand that the inner function is a worker to modify this color and count. So here DFS, you start from a node and with a color. So the node is to be visited and the color is to be assigned, right? So we are going to color node to be C, right? Then the count of this color will be incremented by 1, right? So you see we are modifying color and the count. So notice that both color and count actually are lists. Lists are mutable in Python. Therefore, we don't need to use non-local words. For example, non-local color and non-local count. If you add these two lines, no problem, but this redundant. So I'm going to delete that, right? So then we're going to do the neighbors. So for neighbor in graph node, right? If color neighbor equals -1, it means that this neighbor hasn't been visited yet or hasn't been assigned a color. So because we assign C with the current node with color C, then we need to assign the neighbor with a different color, that is 1 minus C. If your C is 0, so this will be 1. If your C is 1, this will be 0, right? So this will be the inner function. Then we can do a DFS, so we can always starting from node 0 and set a color 0. But actually, you can start from any node and with any color. It does not matter, right? So once you have this, you can return color and the count, right? So now we are going to come to this this one. How to get the same color nodes and the different color and the larger from the second tree. So in other words, in order to get the count, we don't need to do the specific connection, but you need to analyze the logic, right? So graph 1. So we'll be build a graph. So edges 1. So this n. G2 is build graph. Edges 2 as have m nodes. So C1 is the this one, the color 1 list, right? And the count 1 is going to be color graph. So G1 and n. So here I'm going to copy this line and write C2 and the count 2 will be G2 with m nodes, right? So now we have all the information. So first I want to get the maximum same color in C2 in count this count 2, right? There's a larger color class, right? Then basically let's prepare the result. This should be rather straightforward, right? So because we do the coloring, therefore we can easily get the even length path. But the length is the number of edges, right? In the same tree, in tree 1. And then if we connect, so once direct connect, we will have odd distance, right? So then, but anyway, we can choose the larger one, maximum same, right, in the second tree. So if color 1 is larger, so we connect the node at consideration with a node in tree 2 with a different color, right? So for I in range n, first we get the color. So what's the color of this node? So then we get the number of counts in the tree 1. That is n. Let me write it with some redundancy. N same color nodes. So it's count 1. So the current color. So same color nodes will always have even length between each pair. So that's the number of targets, including the node itself, right? If we don't want to include this node itself, we can -1. But in this problem, it says that a node is always a target to itself because we regard this as length 0. 0 is even length. And then we get the larger one. So I just need to actually append n same color nodes, then plus max same, right? So this is actually the because this one also important. M and n is always greater than or equal to 2. At least you have 2 different colors, right? So for example, here, if your I node has color 0, and then in tree 2, the color 1 has a larger count, then you connect the current I from tree 1 with any color with color 0 in tree 2, that would be fine. But if in tree 2, color 0 has a larger count, you should connect the current node with a color 1 node in tree 2, right? In order to use the maximum number. So this way, actually, after we do the coloring, we translate this problem into a linear problem essentially. Therefore, we don't need to try to do the count for each of the nodes, because each number of nodes is like this. It's actually cannot pass the test. So once we have this, so we return the result. Let me first run it. Count is not defined, so let's see, line 48, so count 2, so corresponding to tree 2. Yeah, it passes the 2 test cases. Now let's look at the generic case. Yeah, it passes the generic cases. So here, actually, the code can be accelerated further, but in order to better explain it, actually, I structure the code like this. First, I get the number of nodes in the tree 1 and the tree 2, respectively. And then I build the tree and the colored graph, because we do the same for corresponding to edges 1 and edges 2. So we write 2 utility functions. One is build graph, and one is color graph. So once we have these 2 hyperfunctions, so we just need to call them twice with respect to edges 1 and edges 2 essentially. And then we get all the information, and then we prepare the return. So up to here, actually, prepare return. So up to here, collects information, right? And here, hyperfunctions. Yeah, I structure the code into this 3 part. Actually, if you do this structure, so actually each part is rather straightforward. Then combine together with the logic, especially these 3 items, you get a valid solution to this problem. Personally, I like this problem very much, and that's basically one solution to this. You can try other methods to address this problem. So before we end this video, I want to point out that so we have a YouTube channel which contains more than 1,000 now very carefully prepared videos or practices. So you are welcome to do some practice, use the YouTube channel. If you like it, you can share with your friends so that we can let more people know this channel. And within the channel, we have more than 20 playlists, right, corresponding to different topics, like 2-pointer sliding window, like tree-based, like traversal, like dynamic programming, like a trial, and also say bit mask, and so on. So with that said, I guess that's it for the current video. Thank you for watching.